Hello friends, and welcome to the another lecture on advanced concrete structures, and today we will see numerical on design of sloping isolated footing subjected to a axial column. Okay, so before starting I would like to introduce myself. I am Amey Khedikar, working in the Department of Civil Engineering at Tulsiramji Gaikwad-Patil College of Engineering and Technology, Nagpur. So we will now start with the numerical. I'll read first. Design a sloping footing for a short axial column of size 300 mm by 300 mm carrying 600 kN load. Use M20 concrete and Fe 415 steel. SBC of soil is 180 kN per meter square, and sketch the reinforcement details. So we need to design a footing for a short axial column of size 300 mm by 300 mm. So now we will start with the design. So solution. We will now start with the design. Okay. So firstly, what we have given: size of the footing. I write it down the steps. Size of the footing. Okay. Regarding the calculation of size of footing. So for that we require load from column we required, which is 600 kN. Okay, now 10% of the load coming to it, called self weight of footing, which will be 10% of the entire given load, coming out to be 60. So total load will be this plus this. Okay, so total load will be 660 kN. Okay, then first portion, then second portion will be SBC, called as safe bearing capacity of soil, which is given 180 kN per meter square. Then once we have load and we have SBC, then we'll calculate now area of footing required, which is equals to P by SBC. So what is the value of P? Total load 660 upon SBC 180. Okay, so it is coming out to be 3.667. Okay, it is kilonewton. It is also kilonewton per meter square. It is cancelled, so it comes to the numerator meter square. So now by taking some round value, so we are providing a square footing, of size 2 meter by 2 meter. Just we have make it to 4 meter square, and by taking the under root of 4, it is coming out to be 2 by 2 meter square. So now area of footing will be 4 meter square. Okay, so now then third, design pressure equals to, stands for 1.5 into P by A. So 1.5 into, we have given load 600 divided by area. So it is coming out to be 0.225. Note down the unit, Newton per mm square. It is coming out to be Newton per mm square. Okay. So by this way we have just calculated the size of the footing, area and load required. Okay. So now in the fresh new page I will start with the design. Bending moment. Clear? Now I will start with the bending moment. So before that we should draw the critical section. The critical section where the loading will be critical. We need to try to understand the critical section. Okay, this is your column, which is 300 by 300. This is the entire width in mm. Okay, and this is the shaded portion, critical shaded portion. Okay, this is also 2000 mm. 2000 mm. Okay, now this portion will be 300, so it will be 2000 minus 300, so it will be 850 by 850. So 850 plus 300, 850 equals to 2000. So this is the critical section, the diagram of critical section. Okay, now area of shaded portion. We will calculate the area of shaded portion, which coming out to be area is equals to 2000 base into the top portion height 300 plus, not plus, 300 divided by 2 into the entire height. So it is coming out to be in Newton 977,500 mm square. So it is coming out to be okay. Now upward pressure, second upward pressure from soil on this portion into area. So this value we have previously calculated, that is the design pressure, which is 0.225 into the area. This area we have got shaded portion 977,500, so it is coming out to be 219,938 Newton. Okay, so we have seen the area of shaded portion, we have also seen the upward pressure, we have calculated it. Okay, so next will be centroid of this force from the face of column, at a distance L by 3. So we will see 2B plus L divided by, where this capital B stands for the entire height of the footing, and this small l, where small b is there, it is B. It is B. This small b stands for the cross section of the column, into L by 3. It is B. It is L by 3. So 2B plus B. Okay. So we have 2 into entire height of the footing in plus 300. This divided by 2000 plus 300 is equals to into L by 3, 850. This is the 850 distance by 3. So it is coming out to be 529.71 mm. 529.7 mm. Okay. Hence bending moment of this force about the column face, that will be equals to mu into, now load into perpendicular distance. So we have the upward force, we will write it down, upward, that is the upward force into centroid. So we have upward force, okay, not this is not, we have upward force, this is the upward force pressure. Okay, so 219,938 into the centroid 529.7. So it is coming out to be 116.503 into 10 to the power 6 Newton mm. So centroid we have calculated, and then actually load we have calculated. Okay, So I hope you understood up to the steps up to this. Now I'll move to next page. Now let D be the depth of balanced section. Let D be the depth of balanced section required to resist this moment. Okay, so width of section to be considered as B. See, I am writing this statement because there should not be any confusion between the dimensions, okay, as far as the nomenclature is concerned. And since Fe415 steel is to be used, so from IS you will get that XU equals to 0.48 D. Okay, then you know that from IS 456 MU 0.36 FCK into B into XU limit. Okay, this should be XU limit into D minus 0.42 into XU limit. So now in order to calculate the depth, we need to put the value of XU limit in this equation. So what we will get, I'll write it down here. I'll elaborate the entire process. So equals to 0.36 into FCK into B into 0.48 D into D minus 0.42 into 0.48 D. Again further solving it, 0.36 into FCK into B into 0.48 D into D minus 0.201. Okay, it is coming out to be 0. And further solving it, now multiplying it, okay, it should be D here, then 0.172, just multiply this, okay, 172 into FCK into B into now D, now you just minus it, so it coming out to be 0.8 D square. So it will be 0.138 FCK BD square, 0.3 D square. So now we have the value of MU, that is 116.5 into 10 to the power 6 is equals to 0.138 into 20. And for M20 it is 20, FCK is 20. Then 300 is the value of B, and then D we need to calculate. So by this way we'll calculate, and for one equation one unknown, so we can calculate it by using the calculator, which is coming out to be 375.15. okay, that is mm. You need to do this calculation. Okay, now to make we need to multiply it by 4 by 3. Why? To make footing more flexible, let us take now 4 by 3 into 375.15. so it is coming out to be 500 mm. Okay, 500 mm. Okay, so further step I will write on next page. After calculating the depth at the edges, should be minimum 150 mm. I'll draw the edge, I'll show you. So let us keep the depth, let us keep the depth as h as 200. Why 200? Because minimum requirement is of 150 mm. Okay, so now I will draw it. This is your column. Okay, this is the edge. Okay, so this will be 200. This will be 200, and we have calculated the entire depth, which will be 500. So ultimately it is 300. Got it? Now checking the depth for one-way shear. Checking the depth for one-way shear. Okay, so I will draw the diagram here. In order to understand this, I need to draw the diagram here. So this is our, okay, this is the column. This is your column. These are the edges. Okay, so this is 200, this is 2000. Okay, and we need to, this is 300. Okay, it is bifurcated in two parts. It is 300, it is 200. Okay, and the critical section we would like to identify here. Okay, and finally what we need to calculate. Okay, this is 300 by 300. This is 300 by 300. Okay, we know that it is the 850. Okay, it is 850. The shaded portion. And as far as the critical section is concerned, okay, so it is 850 and it is something here. Okay, it is 350, so it will be 500. Okay, so now we need, it is 2000 mm and it will be 1300. 13, how? 300 plus 500 plus 500. You can see here 300 plus, should be, line should be here, 300 plus 500 plus 500. So now we need to calculate the height. We need to calculate the height. How to calculate the height? So the depth is equals to, now 200, focus here, 200 plus 850 minus 500 divided by 850 into this 500 minus 200, this 500 minus 200. So it is coming out to be, so once again I would like to repeat the state from where I have got this. Okay, so 2000, we need to calculate this depth. Okay, so 200 plus 850 minus 500 into 500 minus 200, so it is coming out to be 323.5 mm. So this height will be 323.5. Okay, clear? So this we have calculated. Then top width, second, top width of the footing, top width means this one of the footing will be 500 plus 300 plus 500 plus 5, it's coming out to be 1300 mm. Okay, so average width equals to 2000 plus 1300 divided by 2. So it is coming out to 1650 mm. 1650 mm. Okay, clear? So I think up to this stage the steps are clear. So we'll now move to next page. Okay. So design moment. So design moment at this section. At this section. So m equals to 0.225. We have calculated this value. Okay. Into 2000 into 850 minus 500 divided by 2 whole square. Okay, so it is coming out to be 275,625.00 Newton mm. 278 is 5. Okay, 500. 500. Now tan of beta is equals to 500 minus 200 divided by 850. So it is coming out to be 0.353. Okay, this is first, and again second we have shear force 0.225 into 2000 into 350. So it is coming out to be 157,500 Newton. Okay, and now tau v is equals to, now we have formula pu minus moment into tan beta divided by d upon b into d. So you can see here 157,500 minus moment 275,625.00 into 0.353 divided by entire depth that we have calculated 5.5 divided by 1650, that is the average width. Okay, that is the average width we have previously calculated into depth 323.5. so it is coming out to be 0.235 Newton per mm square. But the minimum strength of M20 concrete is 0.28 Newton per mm square. Okay, you can see this value from table 19 as 456. Okay, hence the depth provided is sufficient, means okay, sufficient. Okay, the depth required will be sufficient. So now we'll see the calculation for check for two-way shear. So this is okay. Now we'll see for check for two-way shear. Check for two-way shear. So for that we need to redraw the diagram. Okay, so for two-way shear again we need to, this is your footing, these are the edges, this column. Alright, so this is your original column, that is of 300 by 300. So you have this 300, you have this 200 and this 300, total will be 500. Okay, so now these are your as the footing is of sloping, isolated, it is distributing across. So now you will see this. Okay, we'll distribute it now. So it will be a 800 by 800. Okay, and this will be the entire shaded portion. This will be the entire shaded portion. Finally, you have to draw here. Clear? So we need to calculate this now. This D we need to calculate. Okay. And how come it is coming? How come we are taking it as this 800? You might have a question. So this 200, this 300, okay, plus 250 and 250. So it is 800. Yeah. So it will be of 300. It is 250. It is 250. As depth we are taking 500. So it will be distributed to this. So it is of 800. Okay, so you can see here. Okay. So 800 by 800. So this distance will be 250. This will be 250. Clear now? So we need to calculate this. This is of 800. This is of 800. So now we need to calculate this distance. This. So D equals to, now we'll say. So again, D equals to 200. This is 200 plus 850. This entire 850. How much 850? So this 850 minus 250. 850 minus 250 divided by 850 into 500 minus 200. 500 minus 200. So it is coming out 411 mm. So your D is coming out to be 411 mm. That is 411. Okay. And the side of critical section, then side of critical section. Just now I have explained you in the figure, that is 250 plus 300 plus 250. It is coming out to be 800 mm. So I hope this step is clear to you now. I hope this step is clear to you. Okay. So further we will calculate the perimeter of this section. Perimeters means multiplication of all the sides. So it is 4 sides into 800 perimeter. It is coming out to be 3200 mm. Okay. Then depth of critical section. Depth of critical section. So depth of again critical section. Just now we have calculated, that is the 411. So how we have calculated this is the depth of critical section. Okay. Then area of concreting resisting two-way. So this is the area of concrete which is resisting two-way. So area of concrete resisting two-way shear. So what is the area of concrete resisting perimeter into the depth? So it will be whatever answer, it will be mm squared. So answer will be, okay, so that will be the answer, whatever it is coming out to be. Fine. So now the main important part is, when we calculate for two-way shear, the very important part is two-way shear force, also called as punching shear, on critical section, So that design pressure into the cross section of the outer footing minus the column size, minus the two-way shear, I'm just writing symbolically, not supposed to write in the exam, but for the point of understanding I'm writing this. So 0.225 into cross section of this cross section, that is 2000 mm into 2000 mm minus 800, the area in the two-way shear, minus into 800 by 800. Okay, so it is coming out to be 756,000 Newton. 756,000 Newton. Okay, so now we'll next calculate the nominal shear on next page. The nominal shear tau is equals to area. So just now we have calculated 756,000 divided by the perimeter into the area of concrete dome. Just now we have seen 3200 into 411. So it is coming out to be 0.57. But the permitted two-way shear stress is equals to 0.25 FCK, that is 0.25 upon 20. So it is coming out to be 1.118 Newton per mm square. So hence the section is safe in two-way shear. Hence the section is safe in two-way. Now finally we have now reinforcement, a very important part, reinforcement details. We'll see now of reinforcement detail. So the bending moment is resisted by an equivalent. Now the bending moment is resisting by an equivalent section of 300 meter wide and 500 mm deep. Okay, from the equivalent section, our section is of 300 mm, that is wide, and 500 mm deep. So from the expression, U upon 0.87 Fy Ast into D in bracket 1 minus Ast upon Bd into Fy upon Fck. Okay, so now where the B is equals to here the column size and D equals to the depth of balance section. For understanding I'm writing here. Okay, so now putting values here, 116.503 into 10 to the power 6, which is in Newton. So 0.87 into 415 Ast is supposed to be calculated into 500. So 1 minus Ast upon 300 into 500 into 415 divided by 20. So from this equation the Ast, from this equation is Ast, by solving it 645.4 Ast, that equals to 1 minus Ast upon 7228.9. So by we are getting the second order differential equation, the quadratic equation, or you can say a square st minus 7228.9 ast plus 645.4 into 7228.9 equals to 0. So now the AST, by solving the equation in the scientific calculator, second order, so it is coming out to be 716 mm square. Area of steel is coming out to be 716 mm square. 716 mm square. Okay. Now this is to be provided. In a width of 200 mm using 12 mm diameter parts. So calculating spacing 5 by 4 into 12 square 5 square divided by 716, that is the extended it is coming into 2000 the length, so it is across the length it is coming to be 315 mm. Okay, 315 mm. So I can write it here as, so that I can close this here. Provide 12 mm 5 bars at 300 mm center to center in both directions, okay, in both directions. I hope you understood till there. So now check for bond length. Finally check for bond length. Okay, so from IS you will get the formula. Check for bond length. From IS you will get the formula. Check for bond length. Okay, so LD is equals to 0.87 Fy divided by 4 tau BD. Okay, now if you can see the clause number 26.2.1.1 in IS 456. I write it down here. Clause 26.2.1.1. Okay, IS 456. Okay, you'll get a table there. So now we need to put the value of tau BD. So for M20 it is 1.2, but if you can read the further clause there, I will write it down the clause here. For deforming bars conforming to IS 1786, these values which is given in the tables, okay, table number 19, just like for M20 it is 1.2, shall be increased by 60%. This is the clause which is given. Okay, so this 1.2 plus 60% of 1.2, so it is coming out to be 1.92. Okay, so LD development length 0.87 into 415 into 12 bar diameter divided by 4 into 1.92. It is coming out to be 564 mm. 564 mm. Clear? So assuming 50 mm side cover. Okay, so length of bars beyond column face, so it will be 850 minus 500, so it is coming out to be 800 mm. So sufficient bond length is available. Got it? So finally, by drawing the reinforcement details, now we will control the numerical. So just I'll draw here the details of reinforcement. Okay, it is available. So this is our area of footing, okay, which is by 2000 by 2000. Bars we'll see here. Okay, this, okay, so this we know 300. All right, this depth we know, that is 500. Okay, and this is 50 and this is 200. Cover we have put there, so to this it is 500, this is 300, the entire is of 500, where this is 200, it is 300. Okay, so by this way we have concluded the entire design of footing subjected to uniaxial forces, in which we have calculated all the things, checks and necessary assumptions. So I hope you understand the steps and the reinforcement detail too. Okay, so sloping footing for a short axial column we have concluded here. Thank you for patiently listening and watching. We'll meet soon with another lecture.